Okay, this series will wrap up the discussion and the entire chapter on sequences and series. And so we're going to just wrap up Fourier series. Fourier series is what we're going to talk about. The Taylor series can be used to approximate a function that using polynomials. And Taylor polynomials give a close fit to the function near a particular point x equal a. But the error in the approximation can be large at points that are far away. There's another method that often gives good approximations on wide intervals, and it often works with discontinuous functions for which the Taylor polynomials fail. It was introduced by Joseph Fourier, and this method approximates functions with sums of sine and cosine functions, and it is suited for analyzing periodic functions such as radio signals, alternating currents, or solving heat transfer problems. So let's talk about the development. So suppose we need to approximate a function f on the interval from 0 to 2 pi using a sum of sine and cosine functions of this form. So we would say, okay, this function, we're going to call it fn because it's not really the function, it's just a function we're going to use. So fn of x is a0 plus a1 cosine x plus b1 sine x, and then plus a2 cosine 2x plus b2 sine 2x, and so forth, where the nth term is a sub n cosine nx plus b sub n cosine nx. And so this is the notation that you could use to define that particular series. Okay, so here's some things we would like. We actually would like to choose values for the constants a0, a1, and so on, and b0, b1, and so on, that make this function a best possible approximation to the function we're trying to approximate, f of x. So f of nx is the function we're using, and f of x is the function we're trying to approximate. So the notion of best possible would be defined as this. First of all, for fn of x and f of x, they should give the same value when integrated on 0 to 2 pi for all values of k. And then also the product of fn times cosine kx and f of x times cosine kx should give the same value when integrated on 0 to 2 pi for all k. And then fn of x times sine of kx and f of x times sine of kx should give the same value when integrated on 0 to 2 pi for all k values. So actually we put these conditions on there. This is basically just showing what I just said. So if we integrate fn of x from 0 to 2 pi, that should be equivalent to integrating f of x from 0 to 2 pi. And then also, if we integrate fn of x cosine kx dx from 0 to 2 pi, that should be the same as integrating the function times cosine of kx dx from 0 to 2 pi. And if we integrate fn of x sine kx dx from 0 to 2 pi, that should be the same as integrating the function times sine of kx dx from 0 to 2 pi. So now we can determine the a values and the b values such that all the conditions are satisfied in the following manner. So if we were to integrate both sides of this function here, well, what would happen? Obviously, if we integrate this a0 term, we'll get a0 x, and then if you evaluate a0 x from 0 to 2 pi, you'll just get 2 pi times a0 minus 0 times a0, so that would just give you 2 pi times a0. Now you may wonder, well, what about all of the other terms? Well, you can actually show that if you integrate these terms from 0 to 2 pi, the terms will actually cancel out because of the nature of integrating cosine and sine. Cosine integrates to sine, and sine integrates to minus cosine, so therefore they will actually just cancel out. You can show that on your own if you want to, but all of those terms will integrate to 0. So that will just leave the a0 term, which integrates to 2 pi a0. Now, in a similar fashion, if we were to integrate the function of x cosine x0 here, then here's what would happen. We would get from 0 to 2 pi, we would actually get pi times a1. And then if we integrated from 0 to 2 pi of f of n of x times sine of x dx, we would get pi of b1. Now I'll leave you to verify these, but you know, I think if you do this for a few terms for f of n of x, you'll see. So basically, again, all we're going to end up with is the pi a1 and the pi b1 here. And then if we integrate here for any k of x, if we do it for cosine of k of x, where k is, you know, some real number, then we'll get pi times a sub k. And then if we integrate from 0 to 2 pi f n of x times sine, and that should be k of x there as well, sine k of x, we'll get k times b, we'll get pi times b sub k. So again, if you'll just go up here and plug this in here, you'll see that if you plug it in here, then you'll see when you integrate it, you'll get pi a1, and if you plug it in here, you'll see when you integrate that, you'll get pi a sub k. So I'll leave that for you to show. So putting that all together, for this integral, we get 2 pi a0. For this integral, we get pi a sub k, and for this integral, we get pi b sub k. And again, I left out the k, I guess. Okay. Okay, now this f of n function was chosen so that the integrals on the left will remain the same when f of n is replaced with f. So let's go ahead and just replace here f of n with f of x, and we get this equation. And then if we wanted to solve this, we could actually solve this for a0, and a0 would actually be 1 over 2 pi times this integral. And then here, in the second one, replace f of n with f of x, and we're going to get pi, you know, that equals pi times a sub k. And then if you divide both sides by pi, you get a sub k equals 1 over pi times this integral. And then similarly, if you replace the third integral with f of x, then solve for b sub k, you get b sub k equals 1 over pi from 0 to 2 pi f of x sine kx dx. Now, as long as the integrals exist, we can find the coefficients. And if we let n approach infinity and use these rules to get the coefficients of an infinite series, then the result of that series is called the Fourier series for f of x. And it's going to be a0 plus the sum of a sub k cosine kx plus b sub k sine kx as k goes from 0 to infinity. So to find the Fourier series expansion for this step function where f of x equals 1 if x is between 0 and pi, and 2 if x is between pi and 2 pi, then first of all we're going to find a0. So a0, using the formula from above, would be 1 over 2 pi evaluated the integral from 0 to 2 pi f of x dx. Now, since we've got two pieces here, we're going to have to break this up into the two pieces. First of all, we're going to integrate from 0 to pi of the constant 1. So we integrate that, and then we integrate from pi to 2 pi, the constant 2, because we're given that constant from pi to 2 pi. And if you integrate this function and then integrate this function from over the limits that are given here, what you'll get is you'll get 1 over 2 pi times 3 pi. So if you add these two together, they'll actually equal 3 pi. And so you get 1 over 2 pi times 3 pi, which gives you 3/2. Now, to get a sub k, you integrate 1 over pi 0 to 2 pi f of x cosine kx. Well, so you're going to integrate 1 over pi 0 to pi 1 times cosine kx dx, because remember f of x is 1 when you're integrating from 0 to pi, f of x is 1. And then when you're integrating from pi to 2 pi, f of x is 2, so you get 2 cosine kx dx. And it actually turns out that if you evaluate these integrals, you'll actually get 0 for a sub k. Now for b sub k, you have to integrate 1 over pi from 0 to 2 pi f of x times sine of k here. So we're going to get, hang on just a second. Okay, this should have a kx with it, and this should have a kx with it. I just need to check that, but these should be the same as these, sine of kx, and this should be cosine kx. Okay, so anyway, all right, so if we integrate this, if we replace f of x here with 1, we get the integral from 0 to pi 1 sine of kx from 0 to pi. And then if we integrate here, we replace the f of x with 2, and we get 1 over pi times integral from pi to 2 pi, 2 times the sine of kx dx. Now, if you evaluate this integral and add them together, you'll actually get cosine of k pi minus 1 all over k pi. And it turns out that since k pi would just give us multiples of pi, you can actually rewrite this, because if k is 1, then cosine of pi would be negative 1. And then if k is 2, cosine of 2 pi would be positive 1. So that way, if k is 1, you get negative 1. If k is 2, you get positive 1. So therefore, you can actually rewrite this expression as negative 1 to the k power minus 1 all over k pi. So now we know that a naught is 3/2. We know that all the other a values are 0. And then we know our b values, because we can plug in values for b, and we can get that if k is 0, we're going to get just 1 minus 1, which will give us 0. But if k is 1, we're actually going to get minus 1 over pi. So we'll get minus 2 over pi. And then if k is 2, we're back to 0. And then if k is 3, we're going to get the minus 1 again over 3 pi. So we get minus 2 over 3 pi. And then if b4 is 0, and then b5 would give us minus 2 over 5 pi. So if you put all that together and simplify it, you'll get that a naught is 3/2, and then you can factor out the 2 over pi and get that it's minus 3/2 minus 2 over pi times the sine of x plus sine 3x over 3 plus sine 5x over 5, and so forth. And so now you have the Fourier series that we've set out to find. So note that at x equal pi, where the function jumps from 1 to 2, all the sine terms are 0, leaving only 3/2. This is not the value of f of x at x equal pi, since f of pi equals 1. The series also sums to 2 at x equals 0 and x equal 2 pi. Actually, all terms in the series are periodic with period 2 pi. So the value at x plus 2 pi is the same as it is at x, and the series represents the periodic function below. Its domain is all real numbers, and its pattern repeats over every interval of 2 pi. So the series jumps at x equal n pi and has value 3/2, which is the average value of the one-sided limits. So down here you can see the graph of that Fourier series up through f5. Okay, so up through just this term sine 5x over 5. And that's it.